energy, environment, and sustainable development. I'm glad to have you all here today. So, over the past few days, we have explored various aspects of functional materials and their applications in energy and their role in sustainability. I would like to thank all of you for your active participation, and a special thanks to our speakers and coordinators for their excellent presentation. And today we will focus on the topic, the session one, on industrial process of silicon solar cells and the recent advancements as the recent advancements and insight by Dr. M. Jeyanthinath, Professor, Department of Material Science, School of Chemistry, Madurai, Kamaraj University. And similarly, session two on the topic of correlated magnetocaloric and magneto transport properties of magnetite materials by Dr. Kalipada Das, Seth, Anandram, Jaipura College, Kolkata. So we will delve deeper into the latest innovations and research that address the challenges of energy and the environment. I encourage you all to actively engage, share insights, and make the most of the today's session. Let's continue working towards sustainable solutions through the power of advanced nature. And most importantly, I would like to welcome our resource person, so Dr. M. Jeyanthinath, sir. So welcome you, sir. So before start the session, I wanted to give a short brief about you, sir. Sir completed his doctorate on the title of Embedded Semiconductor Nanocrystals Nano Clusters in Oxides from the University of Oslo, Norway. And I completed this postgraduate from National University of Singapore and obtained his PG, the MSc, and a UG degree from Madurai Kamaraj University. And also, the sir has the postdoctoral research associate and industrial experience from various national and then international universities. And he started his career professional career from Madurai Kamaraj University from 2010 onwards. And also the research specialization and the field of research, the photovoltaic, thermoelectric, energy storage, nanoscience and nanotechnology, material science, semiconductor, physics and oxides. And also I have published almost 90 publications. The citation metrics almost 950 plus actually. So research guidance are produced almost five students and ongoing four students there for PhD full time and part time. And also he contributed the research advancement in the funded project also. And moreover, 50 plus journals. He acted as a reviewer in 50 plus journals, and also collaborated with researchers with many universities, national and international. And there are also honors and recognitions with DSC, TAD Award, Raman Fellowship Award, Young Scientist Award, CNRS France Research Fellow, so Norway Research Fellowship Award, and National University of Singapore Research Fellowship Award. Actually. And also sir organized many conference seminars and workshops. So thank you having here, sir. So once again, welcome you, sir. Session is
Thank you, Joseph. Thank you for your kind
yeah, thank you.
introductions. I think I will open up my slides. Before going into, shall we start? Is it okay?
Yes, sir.
Yeah. Before going into the lecture, I just want to thank the organizer for inviting me for this FTP program, and my special thanks to Dr. Sakti Pointy. He is our alumni. And with that words, I'm currently moving on to the topic that I have mentioned here. It's an industrial processing of silicon solar cells. Actually, we all have been looking around and we could see there are many solar cells or panels are mounted in most streets for lights, but we never know or never knew about the what kind of processing exactly the people have been doing in this. And that's with my experience, I thought of sharing it to our fellow colleagues. So that's my motivation for this topic today is. And I would like to acknowledge all the funding agency which I have listed here. Somehow they are contributed in this among this project. You will know, you will see what kind of things maybe they have supported. and some of my colleagues who has been added on with these topics, and they helped me with the learning process of this topic. So with that introductions, I am moving on to the topic. Actually, the outline is classified like this, and you can see I am planning to give and some introduction. You may have heard about a lot of introduction on energy basis. I will be like very shortly. I will give you why do we need this kind of renewable energy systems, or particularly why solar, and give some tips on the semiconductor and its band model. And next, I will move on to the whenever you make any type of device, you need to have some kind of criteria. So for making a solar cells, what are the main criteria one has to follow when you try to make any devices of solar cells? Any kind of solar cells can be used or made with, if we can able to understand this basic criteria for the fabrications. And I will also introduce to some standard process for solar cell fabrication, and once it is fabricated and how it has to be tested. And I also have a very short movie. Of course, I have a very large movie like 30 to 40 minutes, but I will just I have made it for 5 minutes just to give you a flavor of what I have discussed in this lecture. And then I also want to introduce what actual problem that we are currently working on towards the silicon based solar cells. And then I will try to summarize with some examples. And you all know that the energy and environment are essential for sustainable development. And why this is so important? Because of the increase in populations, we were looking at into the global energy need, and the existing energy, that resources that we are available is going to be depleted sooner or later. In the next slide, I will show you how when it will be depleted, and to the to fulfill the human necessity, the worldwide, we are looking for an alternative energy systems, and one among them is this renewable energy systems, which consist of six major different types of methods, and the solar is one among them. As we see here, this is a chart which is given in the German Advisory Council on Global Change, where there is a meeting held in 2003, and they have it clearly illustrate that the existing resources of energy, such as coal, gas, oil, and nuclear, will be deplete, and we will be running out of the energy resources almost around 2050 or even 250. You see the graph is going down. So one has to think about the using the natural resources, which is going to be not exhausted sooner or later. So in these cases, you could see the solar, especially photovoltaics and solar thermal and generators, will have a preference for making the energy fulfillment. So that is what the main goal one has to look at for the solar energy or photovoltaic aspects. And this is a very general energy resource chart where it's giving the primary and secondary. And among the primary and secondary, you could see there's the conventional and non-conventional alternatives. So as you see the current conventional, the main primary sources of conventional sources are fossil fuels and coal, petroleum, and all these or the conventional, and whereas to the alternatives or non-conventional will be solar, wind, and water power, and tidal and ocean thermal, and biofuels would be the non-conventional or alternative energy sources. And to fulfill, or if you think about this alternate or viable options of alternative green energy sources, it has to have a desirable characteristics. So what are those desirable characteristics? It should be abundantly available, renewable in nature, environmentally clean, high energy content, and it should be very low cost and easily storable, economically transportable, conveniently usable, and socially compatible. So these uh, qualities are very essential to be part of these alternative energy green sources. So these six major viable options are explored largely, and solar and wind is widely focused in India. So solar and wind has really taking the first places of energy, alternative energy sources. And we have government has really spent quite a lot of amount of investment to get energy, harvest the energy from these alternative green energy sources. And why should we particularly consider solar energy conversion? As you know, the solar energy is abundant and it is capable of supplying the energy requirements of human race for the foreseeable future. If you consider an our Earth receives almost 173 into 10 power 12 kilowatt hour of an energy from the sun, more solar energy falls on the Earth's surface every day. And if we are able to capture this energy, and we would be able to fulfill the necessity for 16 years at the present rates of utilizations. So this is why the more of the focus are going on to the solar energy conversions. And what kind of radiations are coming out from solar? Because we all know that there is a light energy and also heat energy could be produced from these solar radiations, and this both could yield different type of mechanisms. One, when you consider the heat energy, you could have thermochemical process, and the light energy would yield photosynthesis, photochemistry, and photovoltaics, which is of fuel and materials, and electricity can be produced with these solar radiations. And what is exactly the definition of a solar cell? Solar cell is a basic unit of solar energy generation systems. Electrical energy is extracted directly from the light energy without any intermediate process. The working of solar cell is solely depends upon its photovoltaic effect. Hence, a solar cell is also known as a photovoltaic cell. Simply, you can say that the solar cell or photovoltaic cell is an electrical device that converts the energy of light directly into the electricity by a photovoltaic effect. So this was the most of the different definition of any solar cells. A solar cell is basically a semiconductor p-n junction device. It is formed by joining a p-type or n-type semiconductor materials. Especially here, which I have mentioned, is about the silicon solar cells. As you see here, this is made from a single crystal silicon solar cells, and this is a device that has been, or solar cell, which is made in a as a shown for an example. And before going into the details of the device, we also need to understand the solar spectrum which is coming out from the sun. And the energy in solar radiation comes from the form of electromagnetic waves of wide spectra, and the longer wavelengths have less energy from instant, for instance, like infrared, than the shorter ones which have a visible light or UV. The diagram displays the spectrum of sun rays just outside the entry of the Earth's atmosphere. So if you could see that the visible energy which is coming out in this region is very high, intense, and if we are able to capture this all visible light energy, we could be able to get energy conversion quite viable. But the main thing is we may not be able to capture all the energies which is coming out from the visible energy. Some of them are reflected, some of them are absorbed, and so forth. And the other thing is, if we could capture the whole spectrum, that would be interesting. But it's obviously when it comes to infrared, the heat energy is produced, and there is a photon and photon interactions will destroy the electron hole pair generations, and that is another hot carrier solar cells which is proposed by Coniwear. So we will see what's happening in the later stage. So this is some of the power range of a portable electronics that uses the solar PV systems. Currently in market, you could see these kind of small kits are available, and you could see how much wattage one could need it for using these kind of small panels. And you see that for GPS is almost 100 milliwatts, and for example, for powering laptop computers and camera product chargers, it needs like 10 watts, and power tools and vacuum cleaner and TV would need 100 watts. But if you want to power US homes, that's 10 kilowatt is necessary, and power of a medium of an office building is almost 100 kilowatt, and power of a thousand people village would need 1 megawatt. So we could imagine how much amount of megawatt would be essential, or gigawatt would be essential for a small state one would need to think about that, depending on the populations. So the solar energy potential is, as I said, it's we will have like 1 hour sunlight would be an annual global consumptions, and practical potential would be of 600 terawatt, and it's an infinite supply. And the current need is almost 17 terawatt per year. And the solar energy conversion is, again, I have just illustrated in a chemical formulas that this could be an solar thermal is photons to heat, and solar photovoltaic is photons to electrons, and solar fuels is photons to chemicals. And the solar fuels could be the future interesting research aspects like water splitting, where to generate hydrogens and CO2 reductions. And this is the electromagnetic spectrum, which is and you all know that our solar cells is mostly going to be working in this region, where to 400 nanometers to 800 nanometers. And you could see that here's a comparison for the photovoltaic solar cells and the solar thermal collectors. And these solar photovoltaics uses the visible and IR radiations, direct generation of electricity, whereas the solar thermal collectors uses IR radiations and generates water at high temperatures and high pressure, and it spins the turbine, and you can generate the electricity. And you could see this is a photovoltaic. It needs storage capacities. That's the main drawback of, because it can only operate, or both systems could be only operated only in the daytimes. And this is environmentally friendly, and it's a mature technology, and it has a long lifetime of 20 plus years, fully scalable from milliwatts to megawatts to gigawatts, and generates a DC, needs a converter for AC, and cost competitive, and system not operated 24 by 7. That is the only disadvantage of this. And the solar cells are also again classified into three main generations. And like what we have in cell phones, there are different generations. Similarly, in solar cells has mainly focused of three generations. And what is the limitations of the first generation is it has the limitations of single band gap. As the silicon based technology was matured, so people started with working once they have found that there is a response in photoelectric effect in silicon based materials, they started with silicon, and they made a solar cell device, and they found that it could only capture only the region where the nominal visible regions can be captured. And they found that this is because of their inability of having a band gap of 1.1 electron volt, where it could not scavenger all the other photons coming out from the electromagnetic spectrum. So that was the main disadvantages of the first generations. To overcome the first generation limitations, people thought of thinking of multiple junctions or thin film based solar cells, which could they could make different types of band gaps and capture or scavenge all the photons which is coming out from the solar spectrum, and could capture more amount of photons and yield more efficient electricity productions. But there again, what has the problem is when we try to make a thin film or it's a multi junctions, thermal problems, limitations comes into play, because when it exposed to the light for longer time, it gets heated up, and the phonon and photon will have an interactions, and the recombinations will be formed, and thus the limitations of efficiency was decreased in second generations. So this is was another task where people moved on to the third generation solar cells, thinking of when we could make a nanostructured based solar cells, or dye-sensitive solar cells, or perovskite solar cells, or heterojunction based solar cells. But of course, there they could make nanostructures, but the challenge was to make an uniform or just normal or uniform and distribution solar cells or nanostructures is very difficult, and they could not control the formation of nanostructures in a same manner. So that was the limitations in the third generation solar cells. So this is still going on, and if you want to make a commercial solar PV, The technology has some matured criteria that the main key parameters are efficiency, stability, and processing cost. And if you could see that the first generation solar cell has fulfilled almost all these things, and thus the first generation and second generations has made a commercially viable technology, and this has been sold out in all over the world. And you could see the for example, if you look at the first one, the power generation efficiency is almost in the laboratory level is greater than 20%, and in the module levels it is almost around 18%. And the PV integrated photovoltaics has also been comes into play, and they have this laboratory cells up to 15% and module levels in 10%, 8 to 10%. So these are some of the numbers which are especially for the say first generation based solar cells. And the solar radiation level depend really on the planet Earth's orbit around the sun. As you know, the solar radiation reaches Earth's surface vary daily and seasonally. So depending on that, the generation of electricity will also vary. So that is the main message with this slide. And the direct and diffuse components of solar radiation reaching on the Earth. Normally, we will measure in the AM 1.5 light flux, which is almost around 1000 watt per meter square, or 100 milliwatt per centimeter square. And if you look at this, here is an example of crystalline silicon solar cells with 4.4 kilowatt crystalline solar cell in the rooftop installations, and you could see the energy generations, how it could vary on these distributions in a summer, during the summer time. And here is another comparison on a normal sunny day and for a cloudy rainy day. So you could clearly see that how in the it just increases, and in the daytime it's really saturated, and then it started to decrease when it comes in the evening. So see, similarly, when it is in the rainy day, the cloud is coming up and down, so the oscillation of the power generations is started. So we could not really, that's the only another issue with these solar PV systems. And to give an idea about state-wise in India, for this was taken it from an MNRE systems, and you could see how much it is varied installed in our Indian states. And you could see the Karnataka is having like 7.3 gigawatt, and Rajasthan is almost around 5.7 gigawatt, and Tamil Nadu stands in the third place. And you could see the Punjab has also installed almost 0.97 gigawatt amount of PV installations has been made out. And the global cumulative PV installations is getting increased, and you will see that in the 2020 it's almost 750, and in 2022 it's 1 terawatt. So it's going to be fully going up. And you see the cost of solar electricity kit pad is going to be decreased, and in sooner or later we will be able to use almost the solar powered systems. And with that small introductions, I'm moving on to the exactly in the first generation the materials, which is a silicon. And to give you an idea about the what is a silicon, it has an atomic number of 14, and it has the valence electron. And you have of when you want to make an N type and P type, you have to dope either with boron or antimony or phosphorus, and this could fulfill the PN making of P-type silicon and N-type silicon. And here I would like to skip. That's and you see this is another band gap properties of some semiconductor used in solar cells, and these are some of the materials which are given here. Like this is having a direct band gap and indirect band gap materials, and mostly silicon germanium has indirect band gap with an band gap energy of 1.1 to 0.66, and band gap determines the light absorption properties of the semiconductors. So this with that the silicon was chosen, and because the semiconductor industries has been mostly widely used the silicon materials. And recently people have been moving on to this cadmium selenoid and zinc oxide materials. Whereas when you talk about gallium arsenide or indium arsenide, they are very good material for making solar cells, but the making of the material cost, it's really very expensive. And these are all concentrated solar cells only can be made with this type of devices. And the making of such a big glass to concentrate the solar energy is very very expensive. Of course, their efficiency is almost for more than 50%, but compared to silicon, but silicon demands very less amount of material where compared to this. And the silicon has been proven to be utilized in not only in the terrestrial applications but also in the space applications. And this is another the thickness of the absorber should exceed the absorption length. This is large due to the indirect band gaps, for example in silicons. So that's why most of the silicon solar cells are made in the range of 300 micrometer scale. So that is the main reason. If you reduce the thickness, then the photon will transmit through the wafer. So that's then another issue of that. So you need to use at least 300 or 275 micrometers thick silicon wafers. I think this is some of the informations. The doping really reduces the electrical resistivity, and you see this is an doping impurity concentration for in a silicon, and it makes a p-type and n-type resistivity. And this is a mobility of especially on the silicon, and you can see the electrons and holes mobility when you dope the total concentrations ranges. And with that, I'm moving on to the making of silicon solar cells. And you could here see this is the schematic structure of solar cells. So it contains a p-type silicon and an n-type layer. So how it is made is you take a silicon wafer which is made up of or doped with either with phosphorus or with boron. So if it is doped with phosphorus, then it's an n-type silicon, and then if it is doped with boron, then it is a p-type silicon. In normal cases, we take boron doped silicon wafer, and then we diffuse the phosphorus on top of this surface, and then we can make an anti-reflection coating. Especially the anti-reflection coating is mostly made from silicon nitride layers, which is almost around 80 to 120 nanometers. And then you make metal grids with silver on top of it, and then the backside will be coated with an aluminum cases. And you then these cells are packed in such a way so that it could not destroyed, or it could not be exposed to the atmosphere with dust and so forth. To make that, we will have this is the assembly. So you see the junction box here, and then a back sheet, and then an encapsulation layer of a polymer layer with the front side and back side. But the front side is optimized for the photon incorporation or photon absorption to the solar cell device. And then the glass plate and this frame. Making of a solar cell is doesn't cost much, whereas the assembly and the of this trails and these frames is really expensive. Most of the cost are involved in the assembly, and also the arranging in the terrestrial is the engineering work is really very expensive. And there are some limitations for this solar cell efficiency. You could see the silicon can go up to maximum of 29, and this is called as the Shockley questionnaire efficiency limits. And whereas for the other things, you can the theoretical limitations for this AM 1.5 at 25 degrees C, you can have only is so high efficiency, and depending on the band gaps, you could have different efficient percentages. And the efficiency loss mechanism in a solar PV cell was given here, and these two major losses or subband losses. So as when photon comes in, so you see this limitations here in the band gap, and then the lattice thermalizations, and the other losses are minor, which could be like junction losses and contact losses and recombinations. The recombinations can be removed by when you have high quality or non-impure material, then you can remove these recombinations, and you have a contact with if you could reduce the contact resistance, then that could also increase the transportation. Apart from that, you can also see here there are the spectrum which is not absorbed, and in the spectrums which could be used for thermalizations, and then the extraction losses and available sources are given in this chart. And beyond the Shockley limit, one could think of different types of solar cells which could have can increase the efficiency, and especially as I said, the down converters, up converters, hot carrier solar cells, and tandem cells are have been proposed theoretically, and this is people have been also working and given some laboratory level efficiency, and the reproducible and stability has been not fully understood, and this has not been yet into the market. And this was given by Professor Conybeare from University of New South Wales, Australia. And this is a chart which gives different types of uh, terminologies. Whereas the solar cell, it's a one small wafer which contains all this, and this is called as a solar cell. And when you arrange this cell into different patterns, then it is called as module, and these modules are connected seriously or parallelly, then that is called as a panel, and this panel can be converted into array. So these are some of the terminologies which is used in these solar or photovoltaic forms. And now slowly I am moving on to the real part of the talk. As I said, there is a strong criteria for making any solar cell device. One need to have a material which could absorb the light efficiently. So the first criteria should be the material should absorb the light very effectively. The second one is such absorbed light should be able to transform into charge carriers. So once the photon hits the material, it should generate charge carriers like electron hole pairs should be generated. Once the charge carrier is generated in the material, these charge carriers should transport them or separate them in the material. That can be done by making a p-n junctions. So that's why the n will be moving towards there, and the p will be moving towards in the rear end. And then once these charge carriers are moved, and it can be collected through the contacts. So this is what solar cell criteria comes with the system is. And this is the research best research cell efficiency chart to give you an idea of how many different types of solar cells are available in the world. So people have been working on multi-junction solar cells, single junction gallium arsenide solar cells, silicon crystalline and multicrystalline and nanocrystalline and thin film crystal solar cells, and thin film technologies like CIGS, CDT, amorphous silicon hydrogenated solar cells, and emerging PV and other perovskites based solar cells. And you could see all these are the gallium arsenide based solar cells will have almost around 50% efficiency, whereas the silicon has almost around 27% efficiency. And for third generations, it has been only up to like 18% efficiency has been reported or in the um, iterations. This is for the 2020. And when you talk about on the 2025, you could see the third generation has been pushed further, and you could see it's up to 23% efficiency has been made in the laboratory level scale, whereas for the silicon which has been pushed towards 27%, and this has been recorded in the laboratory level testings. And this chart is made every year by Professor Martin Green. He is from University of New South Wales, Australia, and this is reported in the photovoltaic progress in photovoltaic manuscripts. So he published this every year. If you want to go to understood how the technology has been emerged in the years. Okay, now I'm really moving into the silicon solar cells. And what is a silicon? It's a nothing but a sand, and this could be made. Silicon could be made in different methods. Yeah, you could take the quartz, and then the metallurgical silicon can be get from different routes. You make it as a gas phase, and you can make amorphous crystalline or microcrystalline or polycrystalline silicon thin films. And from the metallurgical routes, you can use the polysilicon, and you can make a Chokolsky crystal growth or float zone crystal growth or multicrystalline, and solar grade silicon can be made. So these are the many different approaches of making silicon material. And if you think about so this is how ingot is made from the silicon production. So silicon grade solar, this silicon is taken, this pieces of junks is taken, and then they are melted into the silicon melts, and then they heat it up into very high temperatures, more than 1400 degrees Celsius in a crucible, and then they make it liquid, and then they start to crystallize using a small crystal, and then left it for a while, and then they can get an ingot. And this ingot is sliced into blocks, and this block is sliced into wafers. So this is how it is made, and this is taken from the scan wafer from Norway. And there are many different companies in Norway that can produce silicon with different kind of impurities and levels, and they can make also polysilicon and monosilicons. So this is what I have already mentioned about the basic criteria of a solar cells. A good solar cell must perform the following operations. So photo generation of mobile charge carriers, efficient charge separations, energy or potential separation and spatial separations, the charge transport to the external electrodes with little losses. So these requirements lead to a simple design rules one should keep in mind whenever designing solar cells of any kind. This is not only for silicon solar cells, this is for any type of solar cells. So now we are moving on to the real picture of the industrial processing. So the normal wafer, whichever we take, it's a plain surface. If you look at the wafer, it will be glad. So that means it will be looking like a mirror. But that means all the lights which is coming in, hitting the surface, is reflected or absorbed. So this is not good. It doesn't fulfill the first condition. So we need to capture them. So to capture the light, what the industrial processes has been done is, you can make an acidic or alkaline etch to make a pyramid-like structure in the top of the surface. And before doing this, you need to etch the wafer and remove the cracks in the wafer. Normally, as I said, the wafer thickness is almost 325 micrometer. After etching the wafer using a chemical polishing etch, you will have like a 275 micrometer. And in the top of the surface of the wafer, you need to make the silicon pyramidal like structure, so that a total internal reflections could happen, and then the photons could be stayed longer time and generate more amount of electron hole pairs in the surface or in the materials. So that is what the process, the first process is done. In another process is to enhance the absorptions. One could also make anti-reflection coatings. So this anti-reflection coating, after this surface modifications, I mean when you after making a pyramidal like a structure, you could coat silicon nitride on top of it, and this could do two things. One is anti-reflection coating. It will act as an anti-reflection coating, and it will also act as a surface passivation layer. So that is an interesting aspect of these two different techniques. And to minimize the reflections, you could make an anti-reflection coating, texturing, and reduce or avoid shading. So that was you need to have you calculative, so that how many number of contacts need to be made. And avoid transmittance. To avoid transmittance, we should have optical thickness, sufficient material with suitable band gap energy is needed. So this is what. the first point. The next point, if one has to the next, once the photon is captured effectively, next you need to you are generating electron hole pairs, and if once the electron hole pairs is generated, you need to have a separation of these energy charges. To do that, you need to have a sufficient doping in the emitter. So the built-in voltage has to be produced, and obtainable open circuit voltage of PN junction solar cell is determined by the doping levels of the substrate and the emitter. So that is main reason why we make a PN junctions. So when the electron hole pair is generated, the generated charge carriers will try to move or it will recombine. To avoid recombining, we need to have a potential, built-in potential, so that the electrons moves in one direction and the opposite directions the holes will move. So this is what the reason while the doping was done. And the next thing is, once the electron hole pairs are moved in, next thing is we need to capture the electrons efficiently in the and transport them to the electrodes. So to do that, we need to minimize the recombinations, avoid or passivate the material defects, impurities, dislocations, and excessive doping, and also need to avoid the shunt resistance. So these are all the things one has to be make to have an efficient charge transport to the external electrodes. And you could see this video, and you will have an idea about that.
To understand how solar cells work, we must look at the components of a solar cell. A solar cell is made out of a thin silicon wafer. When the sunlight hits the silicon in the wafer, photons transfer their energy to the electrons in the material. Electrons with increased energy tear away from the atoms, allowing them to move around in the wafer. A controlled amount of boron has been added to the silicon in the wafer in a process called doping. Because of the boron doping, the silicon will easily get a positive charge. Similarly, the surface of the wafer is doped with phosphorus, and this part of the wafer becomes negatively charged. When electrons are torn free by the sunlight, the electrical field between the positive and the negative parts of the wafer will catch them, and this will cause a current in an external circuit. The efficiency of a solar cell is a measure of how much of the energy from the sunlight hitting the solar cell that can be transferred into electrical energy. We will now look at how the solar cells are made at IFE, but first we need an introduction to how a solar cell works. This is a schematic of a solar cell. The grey area is the silicon wafer. The surface of the wafer is doped with phosphorus. The blue layer is an anti-reflection coating and covers most of the front surface of the solar cell. But to lead the electrons out of the wafer, a grid of metal contacts is placed on top of the anti-reflection coating. The metal penetrates the coating and contacts the silicon below. This is the wafer as it looks when arriving from the producer. It needs to undergo several processing steps before it becomes a finished solar wafers, multicrystalline and monocrystalline. Multicrystalline means that the wafer consists of a number of crystals with different sizes and orientation. Solar cells based on multicrystalline wafers are not as efficient as those based on monocrystalline wafers, which contain only a single crystal. But multicrystalline wafers do not put the same demands on the fabrication process and are therefore easier and cheaper to fabricate. When the wafer is inspected and accepted for solar cell production, they are etched. After the etch process, the next step is to obtain an electrical field in the wafer so that a current may be generated when electrons are excited by sunlight. This is done by making a positive and a negative side on the wafer, or a so-called PN junction.
The wafers usually come with a base doping of boron from the producer.
purpose of the etching is to optimize the path of the light inside the wafer to gain as much current as possible. However, still some 15 to 20% of the incoming solar light is reflected. Now that the PN junction is made, a so-called anti-reflective coating can be put on the front side of the solar cell. This coating helps capture even more of the light inside the wafer. On the front side, the contacts need to be as close to each other as possible to minimize electrical resistance, but at the same time far enough apart to let as much light in as possible. The solution is a grid type of contact. On the back side, it is common to cover the whole area with metal.
To get the contacts through the anti-reflection coating, we need to fire the contacts. We need to heat the contacts up. To optimize the process, we can change this the temperature profile, or we can change the metals that we use.
The solar cell is nearing completion, but we still don't have full control over the excited electrons. To ensure that the electrons don't take shortcuts and create short circuits between the front and back contacts, an isolating trench is made along the edge with a laser, a so-called edge isolation. Now the solar cell is in principle finished, but
Okay, this is what the exact steps that are involved in the process flow, or this is the value chain of making a solar cell device. And then I think when we start up the material, your surface would look like this is an SM image of the cleaved wafer, and you could see how rough it is. And imagine, and this is some of the parameters that has been made, like this is a typical resistivity or between this 1.10^16 ohm or 1 ohm centimeters square resistive wafer will be taken, and these are the size of the wafers, and the thickness is almost 225, and then it will be etched away to remove the damage, either by using a concentrated sodium hydroxide or KOH and substituting rings with deionized water. And this will remove like 5 to 10 micrometer each side. So you can imagine like 225 micrometer will be the rest. And then we will have a texturization by again with a diluted H or concentrated hot H with acidic or base H. And you could see this pyramid like structure is formed. And then you can make an emitter formations. Now because the starting material is only p-type silicon, and to make it an emitter or PN junction, you need to dope it with phosphorus, and this can be done by different methods. And one of the method which you see in the video is by puckle, that is phosphoric chloride gas is passed to the wafer, and then this is heated almost in a high temperature tubular furnace in the controlled ambient for 900 degrees Celsius, and then a glass layer of is also formed during the diffusion of phosphorus, and this glass layer is removed by HF etching. And then this also getters that means what is gettering means is the the impurity which is presented in the bulk material is also sucked up in the n-type layer. So that is what gettering simultaneously happens in that. So the N layer will have all the impurities from the bulk surfaces. And this is one method of passing up the phosphorus into the wafer. Other one, you can spray. This is another technique where you can spray. And this is a belt furnace where you spray it and then put them into the belt furnace at a different temperature zone. So this is another way of making of phosphorus diffusion. And once the diffusion is made, the phosphorus will be diffused in both the ends, also in the rear. So to avoid the shunt resistance, you need to cut out the edges of your solar cells, and then or you can etch them with plasma after diffusions. So this is a very essential to have the removing the parasitic resistance. Once the parasitic resistance is removed, then you could make an anti-reflection coating and the texture on top of the textures, and this could increase almost 30% of incident light into the wafer. And this is done by an plasma enhanced CVD. This is a very custom designed plasma enhanced CVD, and you see this is once the wafer is loaded and after depositing of the silicon nitride with enriched of hydrogen. And this, as I said earlier, this hydrogen would be an interestingly make a passivation of your surface. Also, the defects will be passivated in the multicrystalline solar cells. Once the passivation is made, you could make contacts on top of the solar cell, and the top will be in the where you have coated the silicon nitrate, where in the back side the aluminum is coated, and this bus bars will be made from silver, and in the front side all the contacts will be established with the silver. And this could be done by the screen printing. This is a very old type of squeezing of silver paste into the top of the surface, and once the printed electrodes has to be fired through the silicon nitride layer so that it can establish the contact from the silicon. And you could see the closely on the SEM images how it is looking like. And once the solar cells is made, this can also be tested in different ways. And to understand the contact establishment, one has to go for the core scan or semi lab wafer tester, or to find out the efficiency of solar cells, one need to do an solar simulator with an IV characteristics. And this is the process parameters where to extract the IV curves of a solar cells. With these conditions, one can measure the efficiency, and here is the measured efficiency values, and these are the cell parameters. For this particular case, the efficiency is almost 13.68 percentage, and the open circuit voltage is 0.6, and the current short circuit current is almost 30.53 milliamps per centimeter squares. And you can see these are the necessary tools that need to be used for measuring the solar cells. And a typical IV or for a good solar cells, it should be looking like this, and these are the parameters one could estimate. And if you could fit in this model circuit equivalent circuit for the IV curve, this will be given in this equations. Not only with one single diode, you need to have a double diode so that only it can fit the exact IV characterization that is obtained from this type of fabricating solar cells. And the emitter can be the fingers can be also measured using the core scan type of studies. And this is a general or industrial processing method. And with this, what we are currently working on this, we are trying to replace this blue color, that means the silicon nitride, with the nanostructured coatings. That is what we are trying to process within a couple of projects that we are working on. You could make even different colors with changing the size of the nanostructures, and so that we will be avoiding the silicon nitride process using in the PVCVD. So that is what we are trying. So what we do is we took the silicon, and then maybe we make a N-type layer, and then we try to etch them using different types of etching to make this type of nanostructures, either kind of nanowires or nanopillars or hierarchical nanostructures will be made, and so that it could change the refractive indexes of the layers in a different manner. And we expect that we could absorb more amount of light into the devices. So this can be done by electrochemical etching, that is anodization, or metal assisted chemical etching or stain etching. So this is what can be. And generally electrochemical etching is a well-known technique where you can uh, put your wafer on top of a copper plate, and then you put an electrolyte using an HF based electrolyte, and then you apply a potential between the copper electrode and the platinum electrode in the electrolyte, so that you started to etch the silicon wafers in a certain manner. And for metal assisted chemical etching, you throw out some of the nanoparticles of silver or gold or any other metals and top of the silicon wafer, and you try to use HF, and then it tries start to etch the interfaces of the nanoparticles that are lying on the silicon surface, and then this will make out nanostructures of pillars. And here is one example that we have. It was published from another group, Feng Pen, and they have made silicon images of pyramidal structure formed. And here they have tried to do is they started with the silicon references of reflectance with a different wavelength from 400 to 1000, and you could see it reflects almost 70% of the incoming photon. Whereas when they try to etch it in a different timings, like 40 minutes, you could see that they have almost could absorb almost actually this is in 30 minutes. In 30 minutes they could absorb almost all the photons, so reflectance has been almost the zero. So that is the main thing. And then we try to do it in our laboratory, and we could make an interesting network like structures, and you could see our starting reflectance is almost around 60 or 30, 60 to 30 percentage of reflections after this treatment of the wafer. And then after 30 minutes etching, we could reduce it to less than 10 percentage of the reflectance. And similarly, we were also able to make nano structured wires or pillars, and then this was done by metal assisted. The earlier one was done by electrochemical etching, and whereas this was done by the metal assisted chemical etching. And here also you could see in this region where the main focus of capturing the light region has been reduced drastically. And this nanostructures really helps us to increase, and you could change the absorption properties in the this is another silicon quasi nanowire pores, where also published in the Journal of Material Science and the Material Electronics. So this you could have a reference of this. And also the silicon hybrid nanostructures, where combinations of both quasi porous silicons and the nanopillars combinations gives us another important property of anti-reflecting with the hybrid silicon nanostructures with rod like nanoporous and nano textured surfaces. And this is another, this has not been published yet. This is has been recently we have obtained, and you could say that our nano silicon wires can withstand up to 33 micrometer length of wire of silicons. And this you could see the bunches of silicon nano wires. And this really has reduced quite a lot. But it's interestingly after 30 minutes each or 15 minutes and 30 minutes each, it started to increase. The reflectance increases because it again polishes some of the layers. And another important aspects of making an inverted pyramid or black silicon. So we were trying to make a pyramid like structures with nanostructured layers. And this would also give an future work will yield a better performance of silicon solar cell devices with combinations of our porous silicon and hybrid nanostructures. We were able to make a device, and this in our laboratory conditions. And you could see that our efficiency almost around 7.1% efficiency. And the VOC is really huge compared to the silicon industrial processing, whereas the current is very very low. Of course, this current because of our too many recombination centers, this may not be very low, and you could see very nice diode characteristics is formed in our devices that have been made. And with that introduction, with that, I think I am moving on to the final examples from different types of PV panels with other generations. So this is some of the dye-sensitized solar cells type of examples. This is a kind of various examples with the designs and building integrated. This is a PI uh, building integrated photovoltaics, and you could see you could make a leaf like solar cells. But of course, these are all not available in the market. And you can also have a flexible type solar cells for the thin film based, which can charge back your cell phones and calculators and other things. And here, this is how the normal photovoltaic integrated with the buildings would do it. And just to give an flavor on the what would an ordinary home would need for, so for a laptop and for an led and one fridge and two fans, so this much amount of energy is needed. And for you need to pay like 300 unit per month excluding AC. And if you try to use the solar panels, you could try to reduce the um, units that you need to pay for it. And if you search this solar panels with the specific specifications, and you could see that this price is almost around decreasing. In the initially so 25,000, and now almost it's 18,000. And the people have also been tried to use the tracking systems where to track the sunlight so that it can efficiently produce electricity during the whole daytime. And you could see this is another interesting video where you could close the panel, and then you can the water is circulating. So this is kind of a smart solar tracking systems. And just to give you an idea, in Komudi, there is a solar project which was made by Adani Group, and you could see they were trying to extract almost 648 megawatt solar plants, and this is a really huge plant in Komudi. And here is a comparison of crystalline silicon solar cell and dye-sensitized solar cells made by Fujikura. And you can see the how in the indoor testing uses. And with that, I think I thank the Dr. Raghavendran and Dr. V. Sasirekha, and thank you all for your kind attentions. If you have any questions, I would be really happy to get it. I hope I have taken almost the time.
Sir, thanks for your engaging lecture. Participants, if you have any questions, please type in the chat box. Or you can unmute yourself, you can ask me. Participants, if you have any queries, please unmute yourself, you can ask me.
Namaste, sir.
Yes, sir. Please.
Sir, sir, I have, so it's a kind of a curiosity and enthusiasm. Since from last 2 or 2.5, 3 decades, chemists are working towards this silicon wafers and silicon solar cells. So can we hope to increase this efficiency from around 23-27% to at least 45% in the future decades, sir?
It is not at all possible, sir, because its theoretical limit of a silicon solar cell is almost 31 percentage. Theoretical.
Okay.
We cannot go beyond that, and people are trying to push it up at least 30.
Okay.
Not to 40 to 45. It is not possible, sir.
Okay.
But it's a good question, sir. But there is a limitation, because that's why I started with this three generations. So we have a
Okay.
limitation in the material. So we need to find an alternative option. So that's why people moved on now working on the titanium dioxide. So because the titanium dioxide has a very large band gap.
Okay, sir.
But this again comes into a problem that titanium dioxide as itself cannot capture the light. So we need to have some kind of dye or
Anti-reflective.
sensitizer so that it
Sure.
can capture the light and it can inject the four electrons into the titanium dioxide.
Sure,
So
sir.
we need to have kind of the my personal opinion is maybe in future we will have kind of hybrid kind of structure which could fulfill this thing.
Requirements.
Yeah,
Sure. Sure.
good question, sir.
Why? Because, sir, always when we are teaching this solar silicon photovoltaics in the classrooms,
Hmm.
so usually they ask this question. So from last so many years, people are working towards enhancing the efficiency, but is not able to just achieve that particular efficiency even till today after 2.5 3 decades. But
Yeah.
as you said, it has its own limitation. So
Yes.
under the nature restrictions.
Yeah, because the main thing is the material has its own limitations, and
Sure,
silicon can only, the theoretically speaking, it has only represent up to 31%.
sure, sir. Thank you, sir.
Thank you so
So
much.
I have a question, Srinivas Murthy.
Please, sir.
Regarding solar tracking system, you just showed in the thing,
Yes,
solar
sir.
tracking system. So far, are we making use of the solar tracking system so that we can get the maximum efficiency at 90 degrees? Because the sun keeps on varying, and you are having the panels which is fixed. So how to, could you just give little more insight into the solar tracking system so it can be made better use in the actual field?
Yeah, sir, this is a challenge in engineering and also the cost wise, sir. So
Yes.
normally we are not really interested, because I just want, if we were able to have such a facility,
Hmm.
we could really track the sun and we could be able to collect as much energy as possible. But think about, if we think about the cost wise,
Hmm.
I would not go into the tracking systems,
Okay.
because as I said, making a solar cell is very cheap
Hmm.
because our technology is matured. But the main cost is just to assemble in the form where the tracks and these are made. It costs more than 50% of the total cost. And if you think of using the tracking system, I think we cannot afford, sir.
Okay.
That is
Yes.
that is why the people are trying to fix it in a certain angle where we can capture as much as possible.
And we have gone in a big, large scale for the solar panels in the actual field.
Yes, sir.
But the efficiency goes down with the dust and other things. So it's a maintenance, though we say we are going in a very big way, Adani and other people, but in the
Yeah.
actual field, how much efficiency comes down because of those maintenance, because dust collection and other things, does the efficiency go down?
Definitely, sir. Sir, actually, we visited Adani at Kamudi, sir.
Yes.
And what their main challenge is, dust, sir. Dust is, if you think of cleaning it with a small wipe
Yeah.
without any water, then
Uh,
it is okay. But if you are requiring some kind of water,
uh,
then you are trying to utilize the resources of water, and it is not feasible.
yes.
So the other thing is, sir, birds shit. It
Yes.
makes a stain.
Yes.
And so the people, for example, I think we are starting up to work on hydrophobic glass plates, or
Yes.
no dust-free glasses. So this kind of research activity is going on, sir. But I do not know how, in near future, when we could fulfill this, because the dust should not stick onto the glass.
We have done the solar panels in a large way in all our buildings.
Yes, sir.
So this dust problem is there. As you said, that it should not be cleaned with water because
Mm.
also the water is being consumed. To
Yeah.
just wipe it.
So, definitely, but we cannot do it every day, sir, because
No, we cannot do it every day. Once in a month, it's not
yeah.
possible to do
So
that.
definitely it is going to, because in European countries, or whenever we talk about European or American countries, the air dust is quality is very low or minimal
Mm.
compared to our country. If you just leave the panel near to roadside, you can imagine how much of dust is collected in the panel.
So what is the solution to it? Just neglect it?
No, I think I think the young minds have come up with different ideas of blowing small air into the panels all the time, so that the dust
Okay.
will not. There are many ideas, but how much amount of money one has to put into that, and these calculations is stacking up, and to make sure the some of the engineering kind of aspects has to be come into play, and we have to have a model to make a panel with dust free or maintenance free, because the lifetime of the panel itself is 20 to 25 years. There is no doubt about that, but the only the efficiency wise is going to decrease from morning to evening, and also the dust which is going to accumulate in the panel. If you are able to control that, I think we are much more good enough to have the energy collection.
So we should try to use some sort of blowers.
Yes, sir.
Thank you, sir. I'll try to implement it.
Thank you, sir. Thank you.
Sir, thank you, sir. There is a two question in the chat box, sir.
Please.
One is, good morning, sir. What is the strategy we can follow to get more than 40% efficiency?
I think I have addressed that. For with the silicon, we cannot, but we need to find out a way for having a hybrid type of materials that could go for 40%. And I'm not sure whether we will be able to go with that kind of huge efficiency because of the limitations that we have.
Another one is, may I know the potential about the perovskite
Solar cells. Yeah, I think currently, I think those who are working in dye-sensitized solar cell and perovskite solar cells, compared to dye-sensitized solar cells, perovskite solar cells is better. But the other thing is what type of perovskites, whether you are going with inorganic or organic type of perovskites. So inorganic perovskites is stable, and they are not going to lead into any kind of stability issue. Whereas for the organic type of perovskites, I think we have a big challenge in making it a stability. And laboratory level, definitely we will have a good performance. But when it comes into the play of commercializations, it has very big challenges. So this is what my kind of view on the perovskite solar cells. But of course, in the research aspects, we are kind of limited, and there is no kind of coordination with us to have an good communications to stick on to that this for example, in our MKU, I am working on solar cells. My colleagues, different colleagues, are working on solar cell as well, but we don't have a good coordination, so that one part of the device should be worked by someone else and other part, and if we combine it and come up with a good model of making a device, I think we can achieve a good efficiency. But I also work in all the aspects of perovskite solar cells, and he is also working in all the aspects of solar cells. So in such cases, making a perovskite solar cell for commercialization is very challenge.
Sir, thanks for your explanation, sir. There is no other question, sir.
Thank you so much,
Thank you,
Dr.
sir.
Satyavanand.
Thank you, sir.
Thank you, friends, for patient listening, and thanks for the nice questions. And thank you for once again the SRM for giving me this opportunity. Thank you, Dr. Satyavanand.
Sir, thank you, sir. Thanks for your enlightening lecture, sir. Joseph, sir.
Yes, sir.
Yes, sir. You can
Sir,
continue, sir.
shall we proceed with session 2, sir?
Yes, sir. Yes,
Okay.
yes, sir.
Yeah. Yeah.
I think
Yeah,
I
dear
can.
participants, thank you for yes, sir.
Sir, yes, sir. Yes, sir. Please,
Yes,
sir.
sir. Yeah. So, dear participants, welcome you all to the session 2 of day 5. The topic was correlated magnetocaloric and magnetotransport properties of magnetite materials by our research professor the eminent personality, Dr. Kalipada, Professor, Department of Physics from Seth Anandram, Jaipuria College, Kolkata. So welcome you, sir. We're very much happy to have you here, sir.
Yes.
A short
Hello.
brief about,
Hello. Am I
yes, sir.
audible? Okay.
Yes, sir. Yes,
Sir,
sir.
yes,
Audible,
sir.
sir.
Okay. Thank you very much,
Yes.
Professor Shakti Pandi, for giving me the opportunity to deliver my talk in this platform. Mm, Just 1 minute. I'm sharing. Mm, So it is clearly visible.
Yes, sir.
Sir, it
Visible.
is visible.
It's
Okay.
visible, sir.
Okay, okay. So very good morning to all of you. Again, thanks to Professor Sakti Pandi for giving me the platform. And my topic of this presentation is correlate magnetocaloric and magnetotransport properties of manganite materials. In this talk, I will cover the properties of bulk material as well as nanomaterial. I have listening the previous talk, very nice presentation, and there is the talk was based on the solar cell, and as far as I listen, uh, my talk is also related with the another type of the energy conservation, that is the magnetic energy resource. I will describe it in my talk. First, the plan of my talk is I will first introduced about the magnetic materials, because my talk is based on the magnetocaloric and magnetoresistive phenomena. Both are governed by the magnetic basic magnetism of the materials, and then I will talk correlation signature of the magnetic and magnetotransport properties in the doped manganite materials, and then I will show two uh, novel method by which we can increase the magnetocaloric response, which is very essential for the magnetic refrigeration, and magnetoresistance, which is also application point of view for some bolometric application and sensor application and recording device. And in both cases we will show that the due to the change of the basic magnetic state, ground state of the sample, we can easily tune these two property, and we will get enhanced magnetocaloric and magnetotransport properties. Then I will conclude my talk. So all of we know that the mainly samples are classified, magnetic samples are classified uh, in these three groups: paramagnetic, ferromagnetic, and antiferromagnetic materials. There is also another type of the material, ferrimagnetic, but in my talk I will concentrate in mainly on these three groups of the sample. In paramagnetic sample, we know that there is no long range type ordering, and magnetization or susceptibility is varies inversely proportional with the temperature, and at the low field region, at a particular temperature, magnetization varies almost linearly, which is shown in this picture. However, in case of the ferromagnetic sample, we know that the magnetic ordering is there, and at a particular temperature, below that temperature, that means Curie temperature, the magnetic domains are oriented along the particular direction. If we apply any magnetic field, then it will be directed towards the magnetic field direction, and in the above this Curie temperature, the paramagnetic ground state is found. However, in case of the antiferromagnetic material, the magnetization is initially increases with temperature, and at a particular above the particular temperature, that means nil temperature Tn, it gets the paramagnetic behavior. Now, this is the basic idea of the behind the magnetocaloric effect. Magnetocaloric effect is associated with the magnetic entropy change of a material when it is posted in the external magnetic field region. Generally, in case of when the magnetic field is absent, then domains are randomly oriented But when the magnetic field is present, the domains are oriented along the applied field direction. So if we apply the magnetic field adiabatically, then we know that in adiabatic case, total entropy of the system is constant. That is electronic part, lattice part, and magnetic part. The sum of these three terms should be constant. Now, since the domains are oriented along the particular field direction, hence the entropy should be low in this case when it is oriented at a particular direction. That means to keep this S, that means total entropy of the system is conserved. Electronic and lattice part should be enhanced. That means system will be heat up. This phenomena was first introduced by the E. Warburg at 1881 in case of iron, and this phenomena is called magnetocaloric effect. And this magnetocaloric effect is our future cooling technology. In the previous talk, we all see that the in case of the silicon, solar efficiency is limited 31%. Similarly, in our daily life, we have used refrigerator, fridge, AC, etc. for refrigeration and cooling purpose. But in that case, also the conventional refrigeration, some harmful gases are used, and the efficiency is very less. But if we can able to substitute in future by that refrigeration process by the magnetic refrigeration cycle, by magnetic material, then we can able to get greater in efficiency, about 70%, but still it is in laboratory stage. And the uh, mm, and the physics behind this is schematically given here. In case of the gas compression cooling technology, the similar phenomena can be appear in case of the magnetic material, in use of the magnetic material. That means we can easily heat transfer from heat load to the environment, similar as the gas compression cooling technology. This is the prototype, magnetocaloric refrigeration prototype. And here in this cycle, we have shown schematically that suppose the temperature of the material is T. Now it is adiabatically placed on the magnet. Then its temperature get enhanced T plus delta T due to the change of the magnetic orientation. That means the lower of the magnetic entropy. Now, if it isothermally, if it be the isothermal with the environment, then it will expel heat delta Q amount, and it will again get temperature T stable at that temperature. And now if we remove the magnetic field, then it will cool down T minus delta T temperature. And if it is connected with the heat load at this stage, then it will extract heat from the heat load delta Q amount and get the environment temperature T. By this cycle, we can easily cool down any substance. This is called magnetocaloric refrigeration cycle. Hence, the phenomena is that the main phenomena is the magnetocaloric entropy change. That means magnetic entropy change due to the presence of the magnetic field. So that samples will be helpful for us, for which the magnetocaloric entropy change will be larger. And the since it is associated with the magnetization or demagnetization process at different temperature, it is so we can easily calculate it by the Maxwell thermodynamical relation delta S equals to integration over 0 to h del m del t dh. Hence, if we measure the magnetic isotherm at different temperature, then by the taking area under the curve, mathematically we can easily calculate the delta S, the variation of the magnetocaloric entropy change with respect to temperature at a fixed field, or at a particular temperature the field variation of the magnetocaloric entropy change. There is another procedure by measurement of the heat capacity. If we able to measure the heat capacity of that sample at different magnetic field, then we can easily calculate the total entropy change over the temperature, and from at a particular temperature we can easily get delta S value, and at a particular entropy we can easily get adiabatic temperature change of the material. This is the basic phenomena of the calculation procedure of magnetocaloric effect. Not only the magnetocaloric effect, another important property is also associated with the magnetic ground state for, for strongly correlated structure, for which the magnetism and transport is correlated. Transport means electron transport. The magnetoresistance of any substance can be calculated by the conservative formula the change of the resistance of that material when it is placed in the external magnetic field. For ferromagnetic sample, we know that since the domains are aligned along a particular field direction, so spin scattering will be lower than the antiferromagnetic configuration. This is the giant magnetoresistance circuit, and when the magnetic materials are same direction aligned, then its magnetoresistance will be its resistance will be low with respect to this antiferromagnetic type alignment. In case of the perovskite material, which I will describe just 2 slides later, that generally antiferromagnetic materials, the magnet resistance is very high. However, when it is placed in magnetic field, it become ferromagnet, and due to the field induced transition, and then its resistance become lower. So magnetoresistance can also be influenced by the external magnetic field via the change of the magnetic ground state of the sample. And these giant magnetoresistance have uh, very use in our daily life, that is medical purpose or some biosensor, biomedical application, etc., recording media. Now I will describe some basic properties of the perovskite manganite, because in my whole talk uh, I will talk about the property change in perovskite manganite and property tuned by some chemical composition change in perovskite type structure. Generally, perovskite manganites are, in ideal case, these are the ideal perovskites are electrically insulator and isotropic crystallographic symmetry. But slight distortion of this cubic crystallographic symmetry can provide a huge varieties of the properties, that means ferroelectricity, piezoelectricity, etc. Most fundamental properties of that type of the perovskite material, such kind of LaMNO3, CaMNO3, etc., all are antiferromagnetically ground state, and electrically these are the insulator. But when this trivalent site, such as for example LaMNO3 lanthanum site, if we doped this trivalent site by some bivalent element, that means calcium, strontium, etc., then the valency state of the Mn, which was previously Mn3, in undoped case, the doping percentage of same percentage of the doping will be converted to Mn4 plus, and this introduction of the Mn4 plus ion gives rise new properties. That's very interesting property is the CMR effect in doped manganite. colossal magnetoresistance effect. The magnetoresistance is manifold enhanced in the doped manganite system with respect to its parent undoped compound. Another fascinating property of that doped manganite, nearly 50% doping, is the charge ordering. In case of the 50% doping, when 50% Mn3 and 50% Mn4 ions are there, then Mn3 and Mn4 ions are arranged in a regular pattern. This is called charge ordering, and this charge ordering generally follow the antiferromagnetic type of the ordering. But this antiferromagnetic ordering of the Mn ions can be melted by using magnetic field, X-ray radiation, electric field, etc. And due to this molten state of the Mn3 and Mn4 ion ordering, we can get large MR and large MCE, magnetocaloric effect. Now, in my research work, this is my research work, one of my research work, and where my aim was generally praseodymium calcium manganate, PCMO nanoparticle. It shows the antiferromagnetic type ordering and electrically insulating. However, lanthanum strontium manganate shows the well-known ferromagnetic behavior. Our aim was that if we incorporate lanthanum strontium ferromagnetic nanoparticle within the praseodymium calcium manganate, then due to this presence of ferromagnetic environment, praseodymium calcium manganate can be charge ordering of the praseodymium calcium manganate may be transformed into ferromagnetic in lower magnetic field, which will be the technologically beneficial for uh, utilization of the sample. To do this, we have prepared the sample in basic sol-gel process, which I will not describe here. And the characterization showed that, yes, this is LSMO and this is PCMO. So within the PCMO matrix, LSMO nanoparticle are incorporated. And now we measure its electron transport properties in the presence and in the absence of external magnetic field. This is the basic LSMO. Temperature dependent resistivity shows the, as usual, metal insulator transition, and below this metal insulator transition it is behaves like metallic. However, in case of PCMO, current compound, it shows the charge ordering around 220 Kelvin, and then sharp increase its resistivity and beyond our instrument and reach the resistivity which is beyond our measurement of the instrument by the instrument. And but in case of the core cell type sample, when we placed some LSMO nanoparticle within the PCMO matrix, then the metal insulator transition shift towards the low temperature and resistivity value is get reduced with respect to the PCMO, parent PCMO compound. And charge ordering is still appear around 220 Kelvin. From the magnetization measurement, it is more clear. Now, we have recheck by magnetic property. In case of the LSMO, the half metallic ferromagnetic behavior is clearly visible, and PCMO nanoparticle, the charge ordering melted, but above 5 Tesla. Above 5 Tesla, its charge order state partially melt up to 7 Tesla, which is the limit of our instrument magnetic field. But in case of the core cell sample, the charge ordering of the PCMO host matrix is melted even lower magnetic field compared to its parent compound. And now we know, from the preparation, we know the weight percentage of the LSMO and PCMO. So if we add such weight percentage of these LSMO and PCMO and generate the magnetization versus field response. That will be the red curve, but experimentally we get blue curve. Hence, from this study we can conclude that LSMO and PCMO spins are interact. These are not distinct. Due to the presence of the LSMO within the PCMO matrix, the PCM configurations of the magnetic state of the PCMO is changed. And the main result is given here. Magnetoresistance as a function of magnetic field at a particular temperature, say 100 Kelvin temperature we have measured. And we see that in case of the LSMO or PCMO, in both cases, the magnetoresistance is very low. However, in case of the core cell sample, the magnetoresistance get enhanced manifold. Similarly, at temperature dependence, also showed the same phenomena. That is, in case of LSMO PCMO, its parent compound, it is very low, but magnetoresistance get enhanced manifold in the core cell type sample. And also, the metastable state in the core cell's nanostructure is also given here. At 5 Kelvin temperature, we have measured resistance as a function of magnetic field in case of the core cell type sample. We see that first, when starting the measurement, circled by 1, the resistivity goes down very rapidly. However, this is possibly due to the ferromagnetic LSMO part, and marked as 2. This part is possibly due to the charge ordering melting of the PCMO host matrix, and then it goes to the metallic state and remain in this state. Similarly, magnetic field versus magnetization showed open hysteresis loop due to the charge ordering melting. And if we zoom here, we see a general common phenomena which is known as magnetic training effect in phase separated compound. Magnetic training effect is nothing but due to the magnetic field cycling repeatedly, the magnetic ground state become more stable. That is, the metastable state try to go to the stable one. Here, the antiferromagnetic spin configuration get enhanced slightly due to the field cycling, which is a very common phenomena for the phase separated compound. And this phenomena is still here present. Already we told that the magnetotransport is related with magnetism, and magnetocaloric effect is also related with the change of the configuration of the magnetic ground state. So in case of the core cell sample, we already say that its magnetic ground state modified due to the presence of the ferromagnetic nanostructure LSMO. So magnetocaloric effect. See, the magnetocaloric effect is also get enhanced due to the core cell for the core cell sample due to the presence of LSMO and PCMO sample. The lower value of the magnetocaloric effect is found with respect to core cell sample. However, when the magnetic field is very large, that means 70 kilostate, at that time the PCMO nanoparticle uh, are not in antiferromagnetic phase. It transformed it into the ferromagnetic one and get slightly larger value of the magnetocaloric effect with respect to the core cell sample. But technologically, at the lower field value, if we get larger value of the magnetocaloric effect, that will be more beneficial. That's why we have plotted minus delta S, that is magnetocaloric entropy change with respect to magnetic field change. And we see that in case of the core cell sample, we get a gradual change and a larger value with respect to the PCMO nanoparticle up to 50 kilostate, that means 5 Tesla magnetic field. And from this, we can conclude that the ferromagnetic charge order core cell type nanostructure, we have fabricated it, and we get the magnetoresistance and magnetocaloric effect. Both are get enhanced with respect to its parent compound, praseodymium calcium manganate, that is PCMO. That is one method to achieve large magnetoresistance or large magnetocaloric effect, and there are numerous reports in the literature with respect to this phenomena. And another method I have introduced, which is, can we get the enhanced magnetocaloric and magnetoresistive behavior in spite of using two sample? Can I get it in single one antiferromagnetic sample? Yes. Suppose LaMNO3 is antiferromagnetic insulator, and if we doped certain percentage of calcium, then its phase diagram will be like this. So we have choose the doping percentage 52% and 54%, which is close to this phase boundary, and ground state of the sample is still antiferromagnetic. So now I have made several nanoparticle for 52% doping sample. This is the surface morphology of the bulk sample. ACM, these are all are the scanning electron microscopy picture. This is the bulk sample. This is for 200 nanometer and 25 nanometer, 45 nanometer, 65 nanometer, 190 nanometer, and 240 nanometer. And we have prepared another group sample, slightly composition different, 54%. That is also antiferromagnetic according to the phase diagram, which I have already shown in this circled region. So these all are antiferromagnetic phase in bulk. These are the 54% doping, and the same micrograph for 20 nanometer, 45 nanometer, 100 nanometer, 200, 250, and bulk. A different range of the nanoparticle. Now, for 52% doping sample, we have compared the magnetization as a function of temperature in the presence of very low magnetic field. 150, we see that in case of the 150, magnetization is slightly lower, and 65 they get enhanced, 45 nanometer it get enhanced, and ferromagnetic ground state is pronounced. And for compare one by one, here the response of the bulk sample is given here, and we see that it is antiferromagnetic type ordering is there. This is the charge ordering, and this is the antiferromagnetic ordering. Now we measure the magnetocaloric effect, and we see that in both cases, but here shown for only for one sample for sake of clarity, in both cases the magnetocaloric phenomena exhibit that with respect to the particle size, it is increased with reduction of the particle size. That means in case of the 45 nanometer, it shows the large value of the magnetocaloric effect, and then 65, then 150, and for bulk, it shows the very small magnetocaloric entropy change, and it shows the inverse magnetocaloric effect due to the antiferromagnetic ordering, obviously. So from this study, we can say that with respect to the particle size, magnetocaloric effect get enhanced with reduction of the particle size for antiferromagnetic materials. And this phenomena is not only present in this sample. We have checked another sets of the antiferromagnetic sample, and we see that the same phenomena is occur. Now the question is that why such behavior is appear in nanocrystalline sample, why magnetocaloric entropy change get enhanced. This, to do this, we have studied the in paramagnetic state. We see that delta S is proportional to h square, similar as M versus H graph. However, this is for the bulk sample, antiferromagnetic sample. However, in case of nanomaterials, the M versus H is not linear, even the above of the ordering temperature. Similarly, minus delta S, that means magnetocaloric entropy change versus H square is not linear, but it should be linear in the paramagnetic region. But in case of the nanomaterial, it is some curved. It shows some curved nature. This may be appear, such curvature may be appear if in the paramagnetic state, if there are some ferromagnetic type nano cluster. And we observe that inverse susceptibility versus temperature curve, and we see that 280 is the ordering temperature, but the above the 280 Kelvin, the nonlinear behavior of the nanoparticle is found, but it is absent for the bulk counterpart. So maybe some superparamagnetic nanocluster is present, and to confirm this, we have tried to fit isothermal magnetization curve by modified Langevin function, and we see that yes, some ferromagnetic nanocluster, superparamagnetic nanocluster is there in the paramagnetic state. For the nanoparticle, you estimated the magnetic moment and their variation with respect to temperature, and we see that the lower nanomaterials, lower particle size nanomaterial samples, it is greater. So from this study, we conclude that in a single antiferromagnetic charge ordered material, we can still enhance magneto resistance systematically. Magnetocaloric effect systematically. Now, what will be the magneto resistance? In case to study the magneto resistance, we have measured the resistivity as a function of temperature for all sets of nanoparticle. And we see that with respect to bulk counterpart, in all cases, with reduction of the particle size, resistivity value is reduced. But charge ordering is still there. In case of the nanomaterial, charge ordering is still there, but resistivity value is reduced. Hence, from this, we can easily guess that the ferromagnetic part may be enhanced, because already in magnetocaloric effect we have seen that the ferromagnetic part enhanced, and we have now calculate the magneto resistance, and the systematic change of the magneto resistance with bulk to nano materials is appear. In case of the nanomaterial, the resistivity, magneto resistance is enhanced for all cases. Similarly, for just comparing, we have plotted the magnetization versus field, and we see that with respect to particle size, the magnetization also get enhanced. So underlying phenomena is the ground state of the magnetic ground state change with respect to the particle size. And we see that from experimental data, we see that the ferromagnetism get enhanced as well as magneto resistance get enhanced in a similar fashion with respect to particle size. Now, there are some previous report on that phenomena. Professor Dong already published that ferromagnetic tendency at the surface of the C-type charge ordered manganites is appear, and they also give some insight on the surface phase separation in nano-sized charged manganite. According to their calculation, we can classify a antiferromagnetic nanomaterials into two different regions. One is the core, another is the cell part. And this core part, the still antiferromagnetic ordering is there, but in cell part, some short-range ferromagnetic correlation is newly developed. And due to this developed short-range ferromagnetic correlation, the magnetoresistance and magnetocaloric property get enhanced. According to their calculation, we have also simulate what will be the ferromagnetic volume fraction with respect to the particle size reduction, and our compare it with our experimental data, and it is nicely matched. So this is the one graphical abstract type picture. The all phenomena is given here. In case of the antiferromagnetic nanoparticle, if we reduced the particle size, magnetoresistance get enhanced. Not only the high field, but also it is still present at the lower magnetic field region. So enlarged picture is given here, and this phenomena can be analyzed by using the core cell type nanostructure configuration due to the magnetically phase separation. Another part of the magnetocaloric effect. So already we told that for practical utilization, the sample should needed the large magnetocaloric effect at the room temperature for room temperature application, or the liquid hydrogen temperature for cryogenic application. So we have selected some material for large magnetocaloric effect, which one of the series is lanthanum calcium manganite, when LnCaMnO3, when Ln site is gadolinium or dysprosium. In both cases, we see that the magnetocaloric response is get enhanced manifold, and large magnetocaloric effect is found in the gadolinium calcium or dysprosium calcium sample. Another sample is for the room temperature application. For room temperature application purpose, we have selected the sample such that its ordering temperature should be around the room temperature. That's why we have selected the sample yttrium doped lanthanum strontium manganite, because lanthanum strontium manganite is very well-known ferromagnetic sample, but its ordering temperature is very above to the high temperature 360 Kelvin. To get reduced the ordering temperature slightly lower and close to the room temperature, we have optimized it, and we see that lanthanum yttrium strontium manganite with this composition, its room temperature nearly 300 Kelvin. And we have studied the magnetocaloric effect, and we see that the large magnetocaloric effect and as well as relative cooling power. Relative cooling power is nothing but, suppose it is your magnetocaloric entropy change versus temperature curve, and its maximum value product by its F delta T FWHM, that means full width at half maxima. The product of these two terms is the relative cooling power. So it is also a genuine parameter for practical utilization of the material. So we get in this case almost 400 joule per kg relative cooling power for this yttrium doped lanthanum strontium manganite sample. And the others reported sample is also there with their relative cooling power. So our sample shows moderately large magnetocaloric entropy change. So it can be considered as a good refrigerant material. I have touched the term about the magnetic training effect in nanocomposite. Training effect is mainly due to the magnetic field cycling repeatedly, the growth of the antiferromagnetic configuration, that is from metastable to stable configuration. So it is visible in the nanocomposite core cell type nanostructure very clearly. Here the praseodymium calcium manganite is the core and lanthanum strontium manganite is the cell, just opposite to the first sample which I have shown, where lanthanum strontium was the core, praseodymium calcium was the cell. But here the situation is just different. And for those sample, we have just measured the magnetization with the repeatedly with the cycling of the magnetic field, and we see that its magnetization value get reduced with respect to the field cycling. This is called the magnetic training effect, which is also clearly visible in our phase separated sample. Now I conclude my talk. As far as the experimental results are concerned, we have observed that the remarkable effect in the magnetoresistance and core cell type nanostructure, where the magnetoresistance and magnetocaloric effect both get enhanced. And this enhancement is basically due to the change of the magnetic configuration of its magnetic ground state. And also I have shown some large value of the magnetocaloric effect in case of the gadolinium calcium manganite and dysprosium calcium manganite series. And also for room temperature application, yttrium doped lanthanum strontium manganite exhibits larger RCP and magnetocaloric entropy change, as well as the training effect indicate that the metastable state of the nanocomposite form is get enhanced with respect to the magnetic field cycling and become a stable magnetic configuration. These are the acknowledgement, and thank you very much for your kind cooperation.
Sir, thanks for your enlightened lecture, sir. So
Thank you.
participants, if you have any queries, please type in the chat box, or you can unmute yourself and you can discuss with them. Participants, if you have any queries, please. Any other questions? Sir, I think.
Okay, sir.
Yes, sir. There is no question in this, sir.
Okay. Thank you.
Okay, sir. Thanks, sir. I think participants may understand your lecture fully. I think so.
Okay. Thank you.
Everyone is saying your presentation was very nice, but your presentation was easy to understand, sir. It was very nice presentation.
Thank you very much again.
Okay.
Sir, may I proceed? What are things, sir?
Yes, sir. Please, sir.
Okay. No work is urgent than that of returning thanks. I feel honored to be giving the vote of thanks for today's sessions of the third online faculty development program, day 5. Firstly, I would like to extend my heartfelt gratitude to Dr. M. Jeyanthinath, Professor, Department of Material Science, Madurai Kamaraj University, for his valuable insights on industrial process of silicon solar cell and recent advertisement. Sir, your session provided with us a deep understanding of the intricacies of a silicon solar cell industry, and the way you connected the technological advances with the real world applications was truly inspiring. Your expertise in the field of material science has broadened our knowledge, and we are thankful for the time and efforts you invested in sharing it with us. We are also grateful to Dr. Kalipada from Seth, Anandram, Jaipuria College, Kolkata, for his engaging sessions on correlated magnetocaloric and magnetotransport properties of magnetic materials. Sir, your presentation helped us explore the fascinating world of magnetocalorific effects and their applications, which are pivotal in the advanced material research. We appreciate your detailed explanation and the enthusiasm you brought to this highly technical subject, sir. Thank you, sir. I would also like to take this opportunity to express my sincere gratitude to all the participants for their active engagement in these sessions. Your enthusiasm, thought-provoking questions, and eagerness to learn have made this FTP a great success. Your commitment to knowledge and the professional growth is truly commendable. So thank you once again to all our speakers, participants, and my dear colleague organizers. Let's continue to learn and grow together as we move forward with more such enlightening sessions. Thank you and have a wonderful day again. Thank you, Anandram.
Participants, the feedback link will be shared in this message. Please fill the feedback link. Tomorrow we have the validity function at 9:45. So the two guests will address in the validity function. So please join with us on 9:45 for the validity function. So today afternoon also we have one special lecture at 3 p.m. Please join with the special lecture also. Thank you one and all. So the feedback link is given in this chat box. Please fill the feedback form. Thank you.